Well, good afternoon to everyone. I'm Dennis Wendt, President and CEO of the Franklin Institute. It's a pleasure to have you join us this afternoon for the annual Meet the Scientist program, which is a part of the Franklin Awards Week, which starts today. First of all, I want to thank the PACs and the youth program staff for organizing this great program. You have the opportunity this afternoon to meet some of the most extraordinary men and women of science, and also to understand a little bit about them and how they came into this field. As you know from your research, they are innovators who have often quietly in laboratories through their research have actually changed the way that we think about the world and live in the world that we live in. I think you'll learn about a lot about what's going on today with these men and women. It's an opportunity for you to think about what it would be like for you in the future as you pursue a career in science and technology. And perhaps one day you'll be sitting on the stage as our laureates are. I'd like to thank Mrs. Frank Baldino, Jr., who is our Award Week sponsor, for making this program and those similar to it throughout this week. Before we begin to introduce the laureates, we have a short video that we would like to show for you, and then I'll turn it over to Dr. Frederick Bertley, who is Vice President for Science. So we'll run the video.
When, in the course of human events, a spark of inspiration sets the world ablaze with the fires of enlightenment and puts us firmly afoot on the way of progress, connecting us to one another in ways that elevate all of humankind to equal stations from which to pursue understanding. A decent respect for innovation requires that we recognize those who so affect our receding horizons, using only that to which the laws of nature entitle them, and declare that these inspired few are the architects of our future, and their insights the foundation upon which humankind distinguishes itself from all others. And with this, we hold that truth is not always self-evident, that it sometimes lies deep below the surface, and that the deserving are those who dare to seek it there, and then return to spread the word and say that with a single moment of inspiration, we have truly moved forward. This is our Declaration of Progress, a legacy spanning nearly 2 centuries. The Franklin Institute Awards, the spirit of independence, emanates from Philadelphia.
Well, good afternoon, everyone. Welcome to another great Meet the Scientist program. My name is Frederick Bertley. I'm the Senior Vice President of Science, and it's a pleasure to host all of you again in this great program we do. As you know, this program is part of our awards celebration On Thursday, it is the penultimate experience where we pin the medals on the chest of these distinguished men and women who have actually transformed the very world we live in through their wonderful experiments and discoveries. But the awards week is more than that. We have a suite of programs from Monday night all the way through Friday, this being one of the excellent ones where we showcase these scientists to you. Many of you in the room had the opportunity to see those bio videos. Many of you online have also seen them. But now we're going to soon introduce these great laureates and have you all interact with them. Before I get to that, I just want to recognize the schools that are here in the audience. So when I call you out, I want to hear some true school spirit. So let's start with Frere Charter High School. Not bad. How about Kip Du Bois? Can I hear from Boys Latin? Okay, okay. How about SLA Bieber? And how about SLA Center City? All right. Well, all of you are joined with another distinguished group of students. We actually have some undergraduate students from Drexel University, the Honors Pannoni students here in the front or second row, and some students at the back. Can we hear from you all? Well, this year we're doing something unique and different, actually, and that is we are simulcasting this program around the world. So we have schools in Egypt, schools associated with the Benjamin Franklin Science Corner in Asuncion, Paraguay, schools in Canada, and some schools throughout the United States that are right now watching this program live, and they will tweet, email, and send in questions for you distinguished laureates. That's pretty cool, and we're excited to have that here. With that, I'd like to introduce our two amazing PAC students who are going to shepherd this process of a Q&A. They work in the Partnerships for Achieving Careers in Technology and Sciences. That's one of our signature programs that really takes kids and immerses them in all kinds of STEM experiences. First, I'd like to call up Maya Patton and her colleague, Sam Devine. Ladies and gentlemen, our PAC students.
Thank you, Dr. Bertley. Good afternoon, ladies and gentlemen, and welcome to the annual Meet the Scientists event hosted by the PACS program at the Franklin Institute. My name is Sam Devine, and I'm a PACS explainer and a student at Roman Catholic High School.
Good afternoon, everyone. My name is Maya Patton, and I am a student at George Washington Carver High School of Engineering and Science, and I am also a PACS explainer. Before we begin, let me go over some very simple rules for the day. If you have a question for one of our laureates, please make your way down to one of the microphones at the bottom of each set of stairs and wait your turn. We will alternate microphones. When it is your turn, please state your name, your school, and then ask your question. This year, we'll be streaming the program live. So, when questions come in from our students abroad, they will be read by either Sam or me. Also, we will be live tweeting from here in the theater, so if you have any questions or comments, you can use the hashtag MTS2014. Again, it's hashtag MTS2014. Please try to limit your question to one or two laureates so that we have time to get to as many people as possible. At this time, would you please turn off all cell phones? Are there any questions?
All right. If there are no questions, let's begin.
What's your...
Leave your cell phones on.
Outside of the theater. Okay, so for our people that are watching the live stream, you can tweet hashtag MTS2014, not from inside the theater. Because you're here, you can come down to the mics and ask the question.
Are there any other questions? No? Okay. If there are no further questions, let's begin. We will now introduce our laureates. Please hold your applause until the end of the introductions. The 2014 Bauer Award and Prize for Achievement in Science is awarded to Dr. Edmund Clark. So please hold your applause.
Hold your applause. The 2014 Benjamin Franklin Medal in Electrical Engineering is awarded to Dr. Shunichi Iwasaki and Dr. Mark Kreider.
The 2014 Benjamin Franklin Medal in Chemistry is presented to Dr. Christopher Walsh.
The 2014 Benjamin Franklin Medal in Life Science is presented to Dr. Joachim Frank.
The 2014 Benjamin Franklin Medal in Earth and Environmental Science is presented to Dr. Lisa Talks.
The 2014 Benjamin Franklin Medal in Mechanical Engineering is presented to Dr. Ali Hassan Nefeh.
The 2014 Benjamin Franklin Medal in Physics is awarded to Dr. Daniel Kleppner.
So to start the questions off, I have a question for Dr. Lisa Tokes. What challenges did you face on your global expeditions?
Many. Logistical, financial, how do you get to remote places? How do you fund expeditions to remote places? How do you survive under adverse conditions? And so it takes some planning and some luck and ingenuity. And so you can imagine going to Antarctica is not something you just can do next weekend. So there's a whole host of problems.
Thank you. Go ahead. So if you guys have any questions, make your way down to the microphones
Keep
at the
going.
bottom of the stairs, and then we'll have a PAX representative help you out. Go ahead. So we have a question from Azul Pievapan. This is coming right off of Twitter. So this, I guess, is to everybody here. What inspired you guys to be scientists?
I'll take that one.
Go ahead.
Well, on Christmas Day, when I was 8 years old, my uncle gave me a chemistry set and showed me how to make gunpowder. And from that time forth, I knew I wanted to study science. And it was really, it set the direction of my life.
Thank you.
Hi, my name is Alexander Kubowski. I'm from SLA. So my question is for Dr. Klepper. What are the practical uses you see in the Bose-Einstein condensates?
At the moment, there are no immediate practical applications. However, these condensates give rise to a new state of matter, which is characterized by this very peculiar concept. It's called quantum entanglement. This concept is being applied to a new type of communications called quantum communications. And quantum communication theory is sort of undergoing a golden age right now of interest, which is chiefly theoretical. But somewhere in the distance, people are thinking about quantum computers. One of my good friends who is expert in this field, when asked whether quantum computers would ever occur, he said, there's no law in physics which says that it can't be done, but it can be done. But it won't be done in my lifetime. So that's rather remote. But there are other classes of quantum devices which are being constructed now. It's called cavity quantum electrodynamics or optomechanics, a whole new series of ventures into building a new world where we are starting to make macroscopic, that is, devices that you can see and hold if you want, but which operate on quantum principles. Nobody yet knows where this is going to lead, but I'm sure it will lead somewhere. But really, the inspiration for this research was not to make practical devices. It was try to explore a region which had never been explored before, which is this new region between sort of the quantum world and our own world. And it seems to be a very fruitful world.
All right, thank you very much.
All right. This question is for Ms. Talks and also for Mr. Kleppner. I've heard a couple of other people talk about this too, but on the topic of magnetism, what I've gotten from your presentations upstairs and from the videos that you've shown, is that magnetism is also affected by temperature. So, is it true that the hotter an object, or the hotter a metal, the less magnetism?
Yes, it is true. Yes, so,
And in the like, when you said that the cold magnets would be affected by the Earth magnets, they would hover together. I was just wondering if that had anything to do with the temperature.
yes, it does. As you heat up an object, the two things happen. One is that, actually, there's other people who know this better than me. But I'll see if I can get it right. The individual crystals themselves will become less magnetic until they lose all their magnetism at a point called the Curie temperature. And it's not Marie Curie, it's Pierre, her husband. So that goes on. Also, within a crystal, the magnetic direction is fixed at low temperature because it's too cold for the magnetic direction to change within that crystal. But as you heat it up, there's enough energy just from heat that it can start to change its direction within the crystal. So what happens if you have, say, a lava flow, which you were looking at today, first what happens is it's very hot and there's no magnetism, permanent magnetism, and then you cool it down, individual magnetic moment, the crystals become magnetic, they turn on, but they're not fixed within the rock. And then as you cool it down, the rate at which they're changing slows down until they become fixed over long periods of time, and that's how you trap the magnetic field direction and strength in the rock. Does that help?
Yep, thank you.
Okay.
My question is for Dr. Iwasaki. So, in the video, it said that you have pioneered the field of parallel magnets even though most people have considered it to be, well, not as good as the longitudinal version. And I'm just wondering why did you decide to stick with your idea instead of trying to go with the easy route and maybe becoming famous, well, maybe famous in that particular field?
I have studied very long years on magnetic recording. In my younger days, I studied longitudinal recording at first. And finally, in 1953, about 1953, I invented a very high-density magnetic tape with using iron python, iron cobalt particles. Then I invented, in 1977, I invented the perpendicular magnetic recording from longitudinal to perpendicular. That is a result of the research, long research of longitudinal recording finally, and the approach reached to the perpendicular. That followed Mr. Kuraida. Quite good, very good. And perhaps all technical problems will answer Mr. Kuraida. He's a good friend. Yeah.
Well, Professor Iwasaki is the inventor of perpendicular recording. That was done in 1978, I believe. Yes. And I think the situation that I'm not sure it's a technical question, but the answer I think that you're looking for is the fact that Immediately after that, the entire hard disk drive and magnetic tape recording industry, everyone in the industry started working on perpendicular recording. So he set off everybody's interest in pursuing perpendicular recording. However, by the mid-'80s, it had become apparent that the thing that was limiting the ability to keep increasing areal density on hard drives or on tape was really the spacing between the head and the media, or the spacing between the head and the disk. And I think that at that time, there was no, to the people in the industry, there was not an obvious advantage to perpendicular recording. And so, in fact, the truth is, I think, even at later dates, perpendicular recording media was typically a little bit rougher than longitudinal media. So that made it impossible to get the head closer to the disk or the head closer to the tape. So at least in the United States, where the majority of the industry was, all the companies really stopped working on it. To Professor Iwasaki's credit, he stuck with it. He continued to go to all conferences, continued to encourage people to work on perpendicular recording, and, you know, stuck with his idea that this is the best way to go. He firmly believed it. He kept pursuing it. In 1995, and I did some work on perpendicular recording, none of it technically outstanding in those early days. And in 1995, however, Professor Cherub, who was a faculty member in a center I ran at Carnegie Mellon University, through modeling, he projected that when longitudinal recording reached 36 gigabits per square inch, the areal density, it's a key factor in making hard drives or tape, that the recordings would become thermally unstable because of the phenomena that we were just talking about here, because the bit would become so small that thermal energy would demagnetize it within 5 years. And most people don't want their pictures and other things they have stored on hard drives disappearing after 5 years. So this, now, I have to give you some perspective. At the time, areal density was less than a gigabit per square inch. So we still had a factor of whatever, 40 or 50 to run before the technology had hit its limit. But nevertheless, it alarmed the industry. But that's because the industry was advancing at about 60% a year. 60% a year is a factor of 2 every 2 years. You can work out the numbers. Factor of 2 to the 5th is a factor of 32. Factor of 2 to the 6th is a factor of 64, and now you're in trouble. All right, so that says 10 to 12 years from now, your industry is dead if you can't solve this problem. So the industry was concerned about it. And I held a workshop under the auspices of the National Storage Industry Consortium in the United States. And in real time, in 2 days, we came up with 2 solutions to the problem. One was to change what's called the bit aspect ratio, which is the width of the track to the length of the bit. At that time, it was about 20 to 1. The other solution was to go to perpendicular recording. And everyone walked out of the workshop understanding that those were the avenues to pursue. But the industry pursued longitudinal recording. They pursued going after the different bit aspect ratio, which made, Professor Iwasaki may disagree with this statement, but I think it made sense from the industry's point of view, because they had billions of dollars invested in capital equipment to build longitudinal recording. And they, therefore, continued doing that. Plus, they had an army, thousands of engineers, who know how to do incremental work on longitudinal recording. So they took the path of least resistance, which was continue what they were doing, but change the bit aspect ratio. And if you go look at the bit aspect ratio as a function of time, you'll find that it begins going down after 1995 and gets smaller and smaller. And today it's about 4 to 1, 5 to 1. But then following Professor Cherup's thing, Seagate recruited me to become Senior Vice President of Research and start a research center. So when I went there, we decided that I decided that we would pursue perpendicular recording, which is what we did. And in 2005, Seagate began shipping large volumes of hard drives to original equipment manufacturers like HP and others, and subsequently then they went into high volume manufacturing and to calibrate you. So if you bought a computer since 2006 and it has a hard drive in it, it probably has a perpendicular recording drive in it. There's 600 million of those made a year. Currently, the number increases every year. So that's basically the story. He is the one, he has he deserves phenomenal credit for having stuck with this technology. You got to realize that he believed in it in 1978. It took until 2005 for companies to actually begin making it. And he deserves a lot of credit for keeping it alive throughout that whole time.
I come here the day before yesterday, so I'm not so accustomed in English speech. So, very good friend. Thank you.
Well, it's a pleasure to have an opportunity to talk to you. Thank you.
Nice lecture. Understand?
I have a question for Dr. Klepner. Before you mentioned a golden age of quantum mechanics, how long do you estimate that that'll last?
The end is nowhere in sight. If you're worried that the field may be depleted before you might get some momentum in it, don't worry. The future looks bright, and that's all that I can say.
Thanks.
So before the next question, we have some questions from Twitter. These are from Assumption, Paraguay. The first question is for Dr. Daniel Klepner. What is the thing you admire most about Albert Einstein?
Einstein was wonderful. If you read his original papers, you get goose flesh. Although I don't believe in the supernatural, he seemed to have a supernatural understanding of nature. His clarity of thought and penetration is just inspiring. And of course, his engagement with the world was inspiring too. So he is a unique and elevated person. It's just wonderful to be in the same profession that he was in.
Thank you.
We have another question from Paraguay. This is for Joachim Frank. Is it true that there are cures for diseases like cancer and AIDS, and that pharmaceutical companies are concealing them to avoid losing money?
Well, I don't have any particular knowledge or authority to talk about this, but I wouldn't be surprised.
Okay.
Hi, my name is Michelle Torelli, and I'm a freshman at Drexel University. My question is for Dr. Kreider. Personally, I and a lot of other undergraduates in college don't know whether or not to go to graduate school or not for engineering. Sometimes people say that we will be overqualified and we'll be fine with just a BS or an MS. But I realized in your video that you alternated between university research and industry. What advice do you give to me and my colleagues if we want to go to graduate school or not, and how did you pave your path to do so?
Well, you know, there isn't, in my own view, it's a matter of whether you really want to charter your own course or not. You know, if you have I mean, I don't know that financially you come out ahead, though some of us don't do too bad with having a PhD, but that's not the object. I think the motivation is really, if you have a PhD and you exercise what you can do with it, you can pretty much do what you want to do. I mean, I really believe that's true. It gives you a license to do that. PhD means that you know how to do independent research, in my view. There may be some PhDs who don't know how to do that, but if you're a qualified PhD, you can do that. And I think that that's a freedom that you'll never have with only a BS or an MS. You will be told what to do, unless you're a very unique person, and there are a few with a BS or MS, or Albert Einstein, who didn't even have that, who go on to, you know, do wonderful things. But a PhD does give you license in most communities to have a little more independence in what you choose to do. And I think that's probably the main motivation I would provide for it. So you really have to be interested in the field and want to do your own thing.
Thank you very much.
We have another question from Paraguay. This is for Dr. Lisa Tokes. Could the Earth's magnetic field decrease in strength? If so, what will be the cause of that change?
Well, it is decreasing in strength. Over the last 100 years, it's dropped by about 8%. So it's been coming down for the last probably 3,000 years. It's been decreasing. Before that, it was increasing. So it goes up and down. Why? The source of the magnetic field is deep inside the Earth. It's in the molten iron, liquid iron outer core. And so understanding the processes down there are incredibly complicated. It's numerically very difficult to simulate the magnetic field with realistic parameters. And so we don't know exactly why the field decides to go up or down or flip. And so we can only hope for computers to have enough memory someday to be able to numerically synthesize what the magnetic field might be doing. And in the meantime, we need to understand what the field did in the past. And so that's my job, is to understand what the field actually did. And perhaps someday we'll understand why. Right now, at this point, we don't know why.
One more question from Montreal, Canada. This is for Dr. Walsh. Why are enzymes so important, and how did you go from being a scientist to a businessman?
Why are enzymes so important? So I'm interested in the molecules of life and all the transformations that happen. Sometimes we call it metabolism, sometimes we call it aging, sometimes we call it development. And all the controlled chemical changes that go on from the beginning of life to the end, almost all of them are catalyzed by proteins called enzymes. And so understanding the inventory of what chemistry is possible is, in a sense, understanding what enzymes are, proteins with catalytic activity, and how they carry out the remarkable changes that occur that over time control who we are, how we think, what we do. So I'm been interested in catalysis of chemistry on the molecules of life. As for going from science to business, I would say that my contract at MIT, where I was for 15 years, and at Harvard for 26, is that, and it's typical of the academic world, you can do 1 day a week of non-university consulting. So since 1981, I have done 1 day a week of biotechnology startups or pharmaceutical consulting. And my view is it's been a parallel education to understand what are problems in the real world of medicine and biology, where speaking chemistry, the language of chemistry, is helpful. And also, it enables me, while staying as an academic, to help translate scientific discoveries into new therapeutic agents. In the end, what all pharmaceutical and biotechnology companies sell are molecules, chemicals, for the treatment of chronic or acute disease. So I've been interested in being able to catalyze some new therapeutics from discovery to development to approval. And I've been able to do it, I think, while staying an academic in using the translation as a parallel education.
Thank you.
I have a question for Dr. Tokes. You said that the magnetic field has decreased by 8% in the last 100 years. How much has it decreased between when the lava that you used for the samples solidified and now?
Okay, so I've sampled lavas from everything from the 2010 lava flow back to about 180 million years ago, different lavas. So I'm not sure which one you're talking about because the answer is different.
Okay.
So, in fact, like if you look at, say, 180 million years ago, the field was much weaker than today's field. It's much weaker than average, and it's a very interesting time period for the magnetic field, kind of mysterious. What happened? It seems that the field was reversing quite frequently, and the field was really very weak, less than half of today's field. But 3,000 years ago, the field was much stronger. It was about twice as strong as today's field, and or even higher, almost 4 times as strong in certain places. And so, if you're talking about the 2010 lava flow, then that's a different answer. So the field hasn't changed much.
Okay. Thank you. That answers my question.
Okay.
How you doing? My name is Eric Boatwright, and I'm a student at Kip Du Bois Collegiate Academy. My question is for Dr. Saki and Dr. Crowder, and I realized that you were from 2 different countries. So, like, did you ever compare and contrast like ideas and stuff according to the hard drive?
Actually, Professor Iwasaki and I have known each other. As I said, well, let me just, I think your answer is even broader than that, but I'll illustrate it with his thing. And that is that the magnetism, the research community in magnetics, and by magnetics I mean magnetic data storage and hard magnets and things of that nature, it's a relatively small community. The leaders in the field, we meet every year. There's, at conferences. These are international conferences. There's a couple every year, and most of us attend them, most every time. So we're all talking to each other. We read each other's papers. We give presentations. We eat dinner together when we meet each other at conferences and so forth. Now, specifically in Professor Iwasaki's case, he's, 17 years older than I am, although I'm up there in age too. I can remember visiting him in the early 80s, after he had given his talk on perpendicular recording to begin with. And then in 1987, he and I co-chaired the Intermag conference, which was held in Tokyo, Japan. And that was a great experience for me because I got to really learn about Japanese culture. I've probably been to Japan 20, 30 times in my career, but a lot of them were connected with that conference. So there's not collaboration. To be honest with you, the center that I formed at Carnegie Mellon University in 1983 was founded because the Japanese were beating the U.S. at that time in just about everything they were trying to do. We were beginning to, they took over manufacturing TV sets. They took over manufacturing DRAMs for computers, where they were bringing, Japanese, that's when Japanese automobiles started coming to the U.S. The U.S. was, they were doing a good job. Okay, I'm not being critical of them. They were doing a very good job. So the center I founded was actually, it was Magnetics Technology Center, and it was founded by U.S. companies. In fact, they were so xenophobic that at one time Alcan Aluminum, which is an aluminum Canadian company, wanted to join the center, and our sponsors wouldn't allow them to do it. Okay, so it was founded on competition between Japan and the U.S. Over time, now that competition existed, but we still went to these conferences. We still presented papers to each other. We still went, he welcomed me to his lab. I welcome Japanese all the time to our labs. We exchange information, okay? Over time, by, 87, I would argue, was the peak in how well Japan was doing. Yeah. Over time, the competition declined. And there became more parity. And once parity was achieved, they had centers similar to what we had in the U.S., and they opened them up to U.S. companies. We opened ours up to Japanese companies. And so today, the Data Storage Systems Center, which I founded at Carnegie Mellon, has Showa Denka, it has Hitachi, it has a number of Japanese companies as well as U.S. companies supporting it. So the answer to these questions are they change in time. Reality is science crosses boundaries. I just returned from Russia in November, but I went there in 1980, and as a guest of the National Academy of Sciences in the Soviet Union, and this goes on all the time. Yeah, you're competitors, but science somehow bridges those boundaries, and so you work together, even though, yeah, I'm sure he wanted to see perpendicular recording produced first in Japan, so forth, so on. I wanted to see it done first in the U.S. But we both wanted perpendicular recording to succeed, and it did.
Yeah, very nice relation, I think. Yeah.
Right.
My last question is, even though at first you studied two different things as longitude and perpendicular, is that ever feud at the meetings, like before you were friends?
I'm sorry, I missed the question.
Like, even though y'all were studying two different things, like, did y'all ever feud at the meetings when y'all were younger?
I'm sorry.
Feud. Like,
Were you feuding or were you friends?
Oh no, we were friends. No, we were always friends. No, Professor Iwasaki and I were always friends. There's no question. The competitive situation was more between companies, okay? And so organizations would be set up differently based on between companies and governments. I mean, companies were involved and governments were involved, and those set up the competitions. And, if you're supported by your government or your company, you sort of have to abide by those rules, okay, to some extent. That doesn't mean, but on the other hand, the scientists at a university can cross those boundaries. I was always welcomed whenever I went to Japan. The reason I went to Japan 20 or 25 times is because they were doing leading edge research in magnetic data storage. And whenever I would go there, you know, I used to have some friends at Hitachi Fujitsu, and they would set up, you know, I'd write them and tell them I'm going to come, and could they, you know, set up some visits at these various places. They would not only set up visits, they would host me like Japanese can host someone, and no one in the U.S. can possibly return the favors. They would reassure that there's a car there running me around doing everything. I mean, this is not people feuding, even when I was dealing with the Japanese companies, okay, that supposedly my sponsors were competing with. And my sponsors liked the fact I had this relationship because we were able to cross the boundaries and understand what was, you know, understand technically what was going on.
Okay, thank you very much.
So our next question is coming right off of Twitter for Dr. Clark. How would you know if the model checker has any failures?
Do you mean, how would one know if the model checker itself contained an error? Is that the question? That's an interesting question. Model checkers will often produce a counterexample, and if the specification doesn't hold. And you can actually check the counterexample, you can simulate the counterexample on the original system and observe if that leads to a faulty state. If you want to know whether the specification, you can trust the specification in which the model checker replies true, that may be more problematic because people have taken automated theorem provers and have proved the correctness of model checkers. They're fairly simple programs, and you can verify the correctness of a model checker as well.
Thank you.
We have a question from Paraguay for Dr. Walsh. Through antibiotic research, could it be possible to fight drug-resistant tuberculosis?
So the question is, through research on antibiotics, can one fight drug-resistant tuberculosis?
Correct.
And the answer is every time you use an antibiotic, you encourage the growth of rare resistant organisms which exist in the population. So it's a general statement that when you introduce an antibiotic, its lifetime will be used up by the selection for resistance. Tuberculosis has been the most difficult bacterial disease to treat in history. It's still around. There are more than 1 billion people on the planet today who are chronically infected with tuberculosis, reflecting how hard it has been to find antibiotics that work against TB. Some of you may know there are now strains called multiply drug-resistant tuberculosis, which are resistant to 3 or more drugs. And then there's one called XDR, which is extremely drug-resistant, which is resistant to 5 or more drugs. And those have had a fatality of over 70% in the instances when outbreaks have occurred. So the community, the infectious disease community over the past 5 to 10 years, has changed the way they focus on TB, in large part driven by some global considerations which are not about economics. And I think it's fair to say that there was a drug approved last year which works against MDR-TB, and there are 4 more in late-stage clinical trials. So I think it's reasonable to anticipate we'll get a new group of drugs which are specifically designed and active against TB, and the moment we use them, we'll need the next generation of TB drugs to be waiting in the wings. They're the only class of therapies where the moment you start to use the molecules, you need to design the next ones because they will surely fail.
Hi, my question is for the entire panel. How has your work in science helped you grow as a scientist, a researcher, and an innovator?
So any of you guys could answer that.
I'll take a stab at one aspect of that question. I think that my experience, you got to realize I've gone back and forth. You say I'm a failure at whatever I do because I went from academia to industry, IBM Research, then to Carnegie Mellon University, then I went to Seagate, back into the industry, and now back at Carnegie Mellon again. So I've failed at all of them multiple times. And so I've been to those various places. My experience in terms of getting better at things was that the changes were good, okay? You stay in one focused arena, all right, only focusing on one thing your entire career. Now, I've always been in magnetics, but I've had many broad opportunities because of some of these changes. And in reality, you know, when I was at IBM, I was working on one technology. Companies tend to, if you're good at what you're doing, then you keep doing what you're doing. The nice thing about going to Carnegie Mellon was that I could broaden myself and do a lot of other things. And in fact, because the center supported 7 different departments, mechanical engineering, electrical engineering, computer science, chemistry, chemical engineering, material science, so forth, I got to learn about a whole lot of new things. And it's often at the interfaces between sciences and technologies where the breakthroughs come. So that experience, I think, enhanced my ability to innovate, to see what, you know, was the next thing that would really be valuable and be able to assess, you know, make choices of what I pursued better. Maybe that's part of the answer. I don't know.
So thank you for that. Next question over here.
All right. I'm Anna Sagroon. I'm a student at Science Leadership Academy, and I had a question for Christopher T. Walsh. Is it possible that the cycle of antibiotic or bacteria, antibiotic, antibiotic resistant, new antibiotic, is it possible that that cycle could create a bacteria that was entirely resistant to any antibiotic effort?
I guess the question is, are things getting worse? And I had a former trainee who's now a professor in Ontario, Canada, who decided to do a research project where he sent his students, undergraduates and graduate students, out into their backyards in the Toronto neighborhood to just dig up soil samples and culture bacteria for them and see what they were resistant to. And over 500 different bacterial samples, this was in 2006, the average number of resistances to antibiotics was 7 different drugs, and some soil samples were resistant to 14 different antibiotics. So they coined the term the resistome omics, right? You have to be in omics in the 21st century. So this is about the idea that there are genes circulating in the bacterial population that are resistant to everything that's been seen so far. And the question is just what's the probability they all get collected in one organism? And that really depends, I suppose, on how profligately we use or misuse antibiotics. I think the probability that we can stay 1 or 2 steps ahead by coming up with molecules and molecular scaffolds that bacteria haven't seen is a reasonable prospect. But there is a Russian roulette aspect to it. And of course, that's not just true with bacteria, but also viruses.
Thank you.
Not to be sort of predict a bad future.
We have a question here for Dr. Nathe. Why did you choose to work on dynamic systems, and how did you know there would be applications for it?
What's the question? Can you
Why did you choose to work in dynamic systems, and how did you know there would be applications for it?
Just talk.
It's on. Okay. I started as an undergraduate at Stanford University, and I was working just like you undergraduates in here. I had a friend who was at Berkeley, and he was in naval architecture, and he was a graduate student in naval architecture. And he raised a question where Froude, I don't know how many of you know Froude or heard of the Froude, like the Mach number, Froude for water. And Froude observed in 1863 that a ship whose frequency in heave twice its frequency in roll has undesirable seakeeping characteristics. And so that from that question intrigued me to start studying dynamics and why that behavior for the ship whose frequency in heave twice its frequency in roll has undesirable seakeeping characteristics. So that I started working with that in addition to the problems in approximating the solutions of differential equations, perturbation methods, and in particular, the method of multiple scales, which I developed to deal with these problems. From there, then I spread and expanded into structures, into electromechanical, into ships, into cranes, and so on. The other thing which, once I got into the area, I went in for job which is for small industry. That was in California. One company is called Heliodyne Corporation, which is folded, or right now it has been sold, and Aerotherm Corporation, where we were looking for problems in aerospace engineering, but we were after getting funding. Since small companies, they have to live on funding. And with that, we had to go after anything under the sun, whether it is gun dynamics, whether it's fluid mechanics, it was structures and so on. And from there, I got the broad background to work in the dynamics area.
Thank you. So I want to apologize for the people standing, but right here we're going to have our last question of the day from Twitter. What do you see the future, or I'm sorry, this question is for Dr. Frank. What do you see as the future for cryo-electron microscopy, and what's next?
Well, the future of cryo-electron microscopy is really rosy because for years after developing the technology or using computer programming and so forth, and with ever better electron microscopes, we are now at a point where we are at the atomic level of resolution. And the latest breakthrough has occurred through the invention of direct electron detection cameras. And they brought a revolution into the detection of electron images, which means that we now have images that have higher resolution, higher contrast than was achievable on film. That translates into high accuracy of alignment, of better classification. And we are now, the latest results are reported last year. There are two back-to-back Nature papers in which, for the first time, ion channels have been solved at a resolution of 3 angstroms. This means that all of a sudden the membrane proteins, many receptors, ion channels, and so forth, are fair game to cryo-electron microscopy. In terms of the resolutions that can be obtained for looking at ribosomes, we are now at 3 angstrom resolution. And what it means is, if you compare the capability of cryo-electron microscopy with other methods of structural research, such as X-ray crystallography, in cryo-EM, we can actually image macromolecules or macromolecular machines as they perform their work. So we can really actually track them in their entire work cycle. And this is completely different from X-ray crystallography. So I see, there was a conference which was on, 100 years of X-ray crystallography recently at the Biophysical Society meeting. And at that conference, a number of people spoke, and at the symposium, a number of people spoke. And one of them, who was an X-ray crystallographer, actually predicted that maybe 25 years from now, we won't have X-ray crystallography anymore, and for obvious reasons.
Thank you. So,
my question was for Dr. Talks, and I was wondering if you knew how or why the magnetic field was able to reverse.
No. No, it's a complex system, and I don't know why or how it reverses. I know something about what happens during a reversal. There are records, although the problem is that the reversal occurs over, let's say, 1,000 years, which for geologists is really short. So you need a continuous record of the magnetic field, and we don't have Seagate hard drives in the Earth. And so you're stuck with basically 2 kinds of records. One is piles of sediments, like mud in the deep sea or in a lake or something, and it has to span the time period of the reversal. Or you have stacks of lava flows, like on Hawaii or something. And these 2 different records are quite different in their properties. One is low resolution but continuous, and the other is high resolution but very discontinuous. So we don't have perfect records, and the reversals records are themselves extremely rare. So you have to, I didn't, because I thought it was looking for a needle in a haystack, but some of my friends have spent their lives looking for these reversal records, and now they're old and gray, and they have maybe 1 or 2. So so we don't know exactly what happens during a reversal, and then that makes it, we need records from all over the world to really describe the field, how it changes. And so we don't really even know how it happens. And until we understand exactly what happened, I don't think we're going to understand why it happens. Until the Seagates of the world can give us more memory and faster computers, we can simulate the problem, but that's not going to be, certainly not in my lifetime, where the computers are big enough and fast enough to do the job for us. So I'm sorry, I don't know the answer. However, it's a great field to get into because there's a lot of open questions.
Thank you.
So thank you to all of our panelists, and thank you for all of your questions. I'm just going to hand it back over to Dr. Bertley. All right.
Well, thank you all very much. First, I'd like to thank Sam and Maya for facilitating the program. I'd also like to thank the following teachers and administrators: Matthew Van Kerberg, C. Johnson, Christopher Zakacki, Jason Porter, Nate Petatino, Trey Smith, and Jasmine Bullock for organizing a lot of our area high school students to participate. So thank you all. I also would like to thank Suzanne Richelieu from Drexel University and the wonderful partnership we have there on bringing some of your great honor students and other students from your undergraduate cohort. So thank you very much. Of course, I want to thank the Franklin Institute staff. I won't name all of you, but from theaters to operations to everything for putting this together. We really, really appreciate this. Second to last, I'd especially like to thank Claudia Rodriguez Ortega. She is actually based in Paraguay, and she's our partner that organized all those students and all those great Paraguayan questions that you heard. So if you're still on board or online, we thank you over there from the south of the continent. And last but not least, I'd like to thank our esteemed panelists and distinguished Benjamin Franklin laureates for the year 2014. We are having a reception upstairs to the left in what's called Lower Harcourt. The panelists will be around for another half an hour, so please feel free to come and get some refreshments, and you can ask them some of the questions that you didn't get a chance. With that, I'd like to thank you all and have a wonderful rest of the awards week and Philadelphia Science Festival the following week.